Alrighty. Today we'll be talking about lecture 5, instruction level parallelism, and we'll be going over the different ILPs and approaches and other stuff as well. Let's just jump right through it and let's just talk about what is an ILP at first. ILP and its approaches. Okay, so ILP is an instruction level parallelism and measures how many instructions can be executed concurrently. There are two types of it. There's a static approach and there's a dynamic approach. The static is mainly regulated in terms of software. The dynamic is regulated in terms of the hardware. The software, the compiler decides which instruction is to be executed in parallel, while as the dynamic approach, the processor is the one that decides which instruction executes in parallel mode. Excuse me. Um, Over here we have a small example showing an ILP example. That is a dynamic approach and how it is done. Next, we'll be talking about a new thing which is pipelining. Pipelining, it's a concept which allows overlapping um, of an execution to improve performance. So there are stages to it. There's a instruction fetch, an instruction decode, an execution, a memory access, and a write back. And there's also the two types. There's the latency and there's the throughput. Latency is the time to complete one instruction. The throughput is the number of instructions completed per unit time. Over here we have a pipelining processing, showing that how it goes. It goes through two input and then from there into a multiplier and then to an adder, and then it gives us one output, and it also has another input on the other side. And this is just like a pipelining process example. Next, we'll be talking about superscalar and VLIW architectures. So, what are superscalar architectures at first? There are multiple execution units allowing multiple instructions per cycle, whereas the VLIW stands for very long instruction word, and the compiler packs multiple operations into a single long instruction word. Well, how are they different? The superscalar, the hardware handles parallelism and there's no need of recompilation, whereas in the very long instruction word, the compiler handles the parallelism and requires the recompilation for different architectures. As here in the example on the slide, it shows that the VLIW has a goes through a shorter process than a superscalar. However, the superscalar does not require any recompilation, which is an advantage over the VLIW architecture. However, both are used in different operations. Okay, next, we'll be talking about in order and out of order execution. The in order execution is pretty much the instructions are executed in the order that they appear at the program. Whereas the out of order execution instructions are executed as soon as their operands are available, not necessarily in program order. However, here's the thing. The out of order execution can be beneficial and can have an advantage over the in order because of a the fact that there is no stalling happening in the process of the pipeline, and it would require less timing at the end of the day compared to the in order execution. Next, we'll be going over register renaming. But the register renaming, like for example, over here we have a problem. A write after read and a write after write. Those both depend on like their dependencies limit the ILP. The solution to that is to register renaming assigns each new value to a new register, breaking the false dependencies and increasing also the parallelism. For example, over here, this is a process that it can go through. Instruction is allocated entry J. If yes, it will go through an instruction as a designated register. Yes, okay, it will have a map to a ROB entry. Yes, then you can rename it, or it can go through another series and then it would end. So the register renaming is pretty much like the whole thing behind it is just to break the dependencies and increase the parallelism. Next, we'll talk about the pipeline hazards. We already talked about two of them, which are the write after read and write after write. Um, Over here, there's data hazards, and there's also control hazards and structural hazards. All three of those are the hazards. Under data hazards fall the read after read, read after write, write after read, and write after write. Those are dependencies between instructions, whereas the control hazards are caused by branch instructions. As for the structural hazards, they have conflicts in resources. Next, we'll be talking about the dynamic instruction scheduling. The purpose behind this is to pretty much reorder the instruction in execution to reduce stalls. Like we said, it pretty much falls under the out of order execution as well. The benefits of this is that it has a far way more efficient execution, and it handles the dependencies, and it tolerates any delays. Examples for it, there's the scoreboarding scheduling, and there's also the Tomasulu's algorithm. The Tomasulu's algorithm is used uh, to reserve stations, and it's also a common data bus to handle out of order execution. Over here on the side on the figure, we have an example of the Tomasolo's algorithm and how it works. It goes through an instruction queue, and then it goes through an addition or subtraction reserve, maybe a multiplying or division, and then it all falls back to the common data bus. And then from the common data bus, it would go back to the register bank or to the memory, and it will reoccur again. So it's a very efficient and um it's a very efficient, and it tolerates delays in terms of execution. Next, we'll be talking about branch prediction. And as for branch prediction, the purpose behind this is pretty much just to reduce the penalty of branch instructions. There are two types of it. There's a static prediction, there's a dynamic prediction. The static prediction is based on fixed rules, like always predict, not taken, for example. Dynamic prediction uses historical information to make predictions. So it pretty much is like an AI system where it learns from itself. There's techniques for the branch prediction, and there's a bimodal predictor, and there's a two-level predictor. The bimodal predictor uses a single bit, whereas the two-level predictor uses a pattern history. Over here on the side, in this figure, we have an example of a dynamic prediction where it pretty much like learns from itself. Okay, predict taken. Okay, it would take it, and okay, and then the process will go over and over again, just like using historical information that have occurred once before to predict the next outcome, pretty much. That was it for today regarding ILPs. Just an ILP overview. We went over and what's the definition of it, and what are like different approaches that you can approach it through. We said that there's a static way or there's a dynamic way. As for pipelining, we went over the concepts, the stages, and the impact on the performance. The superscalar and the VLIW, we said that those are both like also another types of executions, and take like there's a hardware and there's also a compiler parallelism when it falls down to those two. We also talked about the in order and the out of order executions and the techniques that are used with those to increase parallelism and to avoid any stalling in terms of out of order execution. And next we talked also about register renaming, breaking dependencies to improve the ILP, and that also falls within the out of order execution. We talked also about the three types of pipeline hazards, And we also talked about the dynamic scheduling and um, using their techniques such as the scoreboarding or the Tomasulo's algorithm. And last but not least, we talked also about the branch prediction and how we can reduce controlling hazards within them. Um, that was pretty much it for today regarding our slide. I hope this was beneficial and I hope you guys have a good day. Thank you.